my gosh, I forget 3 times a week.
All right. Good morning, everyone. Welcome back to Physical Geology 1403. How was the weekend? I've got two thumbs up, thumbs down. Oh, I'm sorry. Actually, I had a kind of a rough weekend too.
How did you like the Super Bowl?
I loved the Super Bowl. Who doesn't love seeing someone dethroned? Right? I couldn't care less about the Eagles, but it was a little satisfying to see the Chiefs unthroned.
It was. We were watching it, like my family was all watching it together. My mom was like, I kind of feel bad for them because like it showed the two pictures of Patrick Mahomes and Travis. I was like, I don't feel bad at all.
Yeah,
I have no remorse.
Yeah, and so soundly put down too.
Yeah.
I'm sorry for all you Chiefs fans if you feel like your team underperformed there. I don't know what the Eagles had for dinner that night, but they put the smack down. Huh? Whatever was looted off the streets of Philly? No, that happened later.
That is.
That happened later. Let's see. Anything of note? Anything interesting?
Google Maps changed the Gulf of Mexico to the Gulf of America.
They finally did
No one
it.
told them. They just felt like it. No one told them they had to.
That's such a random yet.
Let me look. I want to see. Google Maps. Woo. Where you going, kid? You're all wrapped around the microphone. All right. Zoom out here. There it is, Gulf of America.
Zoom out. It says Gulf of Mexico, but then Gulf of America is red.
No, it just says Gulf of America, bro.
Some more.
Zoom out.
Zoom out. Keep going.
Gulf of America.
Whoa.
Did it finally like completely change over? Let me check.
Apparently.
Drift over into Mexico. See if that. like hover over.
Oh yeah,
Mexico
no, it's
slightly.
completely Gulf of America now.
Yeah, no, Gulf of America.
I guess
no.
do they have the parentheses?
This
the parentheses
morning.
up to.
Was it this morning? Yeah, this morning it still had Gulf of America in parentheses and still said Gulf of Mexico. But now she's.
I guess they
Oh no! Look,
decided to commit.
They said we're committing.
Well, as long as we're talking about bodies of water.
Can you keep zooming out potentially?
it's still on here.
Yeah, it's still out there. Zoom out more. There it is.
Oh yeah, okay, there we go. Gulf of Mexico, parentheses, Gulf of America. So if you look at if you think small, it's Gulf of America.
Oh, that reminds me of something.
Okay, all right. Here's something interesting. Gardi Sugdub. You ever heard of the island of Gardi Sugdub? As global warming continues, sea levels rise, right? It seems very small to us, only a couple centimeters a year, but it adds up. So over the last few decades, some low-lying islands in Indonesia and in the case of Gardi Sugdub off of Panama have actually gotten flooded out. This is the island of Gardi Sugdub now.
Oh.
All of that used to be island that people could live on, but over the last few decades, it's gotten slowly flooded as the ocean levels are rising. They just finished evacuating the rest of the island not long ago because those streets are all covered in water. You look at pictures of inside people's homes, even though they're on stilts, the water has risen to the point where it's in the house. There's water on their floor. Completely unlivable now. A few people actually still live there, though. They refuse to leave. They said if the island goes underwater, so do I.
They go down with the
They'll go down with the island, I guess. So, yeah, so that's the situation. Anyone who thinks it's not a real thing, you just tell them, look up Gardi Sugdub. to the nation of Panama, I'm sure they do. I doubt Panama has officially announced we are abandoning this island. They've moved everyone who would leave off, but it's still part of their nation. Okay. All right. Anything else we want to talk about? Anything we want to bring up? There was a let's see, 7.6 earthquake this weekend off of the Cayman Islands. Yeah, wow. Pretty far from anyone, but still pretty sizable. Nothing?
I don't think there's much that happened this week. Our weekend. Besides,
Nothing that happened this weekend besides the Eagles deal.
And
Yeah.
the Kendrick Lamar halftime show, which was really good.
I'm not a fan.
Really?
No, I can't relate to music that's all about dissing someone else. It's not relatable to me, so I don't enjoy that kind of music.
What about the thing with the paper straws?
The thing with the paper straws.
Oh yeah.
I don't know what he's talking about. Anyone want to explain that?
I don't know.
Was it a ban?
A ban on paper straws? Yeah, they are the worst. Paper straws are the worst.
Well, why ban them?
Why ban them? Because they're the
Why?
worst.
Like that's actually the most useless order ever.
Yeah, but if not, restaurants are gonna sell them or put them with people whenever they're ordering drinks.
Yeah. I did see that Trump is planning to tell all the mints to stop making pennies. Which, I mean, how many of you actually use pennies?
Well, they actually are banning. paper
It
straws.
actually,
That's actually insane.
actually, if you can't put up with paper straws, that's actually a skill.
That's actually
That's
insane.
actually a
No. That's
That's something
it's
that
been in
Trump
your
is
drink
pushing.
too long issue, and that's
Paper
outside of
tastes-
my control
paper tastes
sometimes.
Fine. Paper's fine.
No. I don't like tasting the
Get a
paper
second,
though.
Okay, paper tastes awesome. You've never eaten paper?
They should make flavors.
You ate raw.
No, there's actually
No, you've never tried paper.
paper contains chemicals that are not good for you, bro. There's actually a whole disease that can turn into a genetic problem that comes from eating paper. I'm sorry if I just ruined your favorite snack. All right. We good? Should we begin? We actually do need to begin because we're going to finish the lecture on time at 11 o'clock today. I have a meeting in Midland at 11:30, the West Texas Geological Society. We meet once a month, and I need to be there for the one today. I'm talking a little bit about some of the research that I'm doing, and hopefully I can get some funding out of it. So, okay. Today we are talking about Lecture 8. Yay, Module 2. How was the exam, by the way? I hope everyone took it. I know, okay, to be honest, I have not looked to see how many of you all in this room have not taken it, which means that you have until this afternoon, really, technically, before I notice that you haven't taken it when I get back from my meeting. For my online students, I've already started grading your exams because there are more of you. I started your class first. And I noticed that like 7 people on my online class have not taken it. So it's going to be late now, but a late exam is better than a 0 on your exam, right? So please go ahead and take that. Yeah, how was it? Hard? Was it difficult? Did it seem like we had, harder than you expected? Okay, that's fair. That's probably about where exams should land. Harder than you expect, but still doable, right? They are meant to be the more difficult assessment because they are the summative assessment, not a formative assessment. They don't help you learn. They assess how much you have learned, right?
Yeah.
Okay. Well, I hope that y'all are somewhat confident about it, and if all goes according to plan by the end of today, I should have all of those graded. I have a soundtrack now. Did I tell you guys that? I have a DJ. that was I didn't realize I needed one. That was your audition for being my life DJ, right? Yeah. All right. So let's begin. We're going to start off by talking about mass wasting, and then we're going to move into a conversation about running water and groundwater. Anyone remember what mass wasting is?
Weathering by gravity.
Not weathering by gravity.
Erosion.
Erosion by gravity. Remember, weathering is the breakdown of material and erosion is the transport of that material. Gravity doesn't break things down, but it does move stuff, right? How does it move stuff?
Whoa.
Whoa, that was violent. Stuff falls. Newsflash, that's gravity. All right, why does stuff fall? Why did that remote fall? If I jump up and down, why do I fall back down?
Earth's gravitational pull.
What is gravitational pull? Explain gravity to me. Why is there a pull?
We don't know.
What, you guys haven't taken interstellar physics? Come on, that's not a prerequisite to my class.
It has more mass. It has a lot of mass.
Okay, exactly. It has to do with mass. All things with mass have a gravitational pull. Gravity is still something we're actually trying to figure out. We understand that it works. We're still trying to understand the quantum mechanics of how. But right now, it is a law, the law of gravity. Everything with mass has a gravitational pull towards itself. Towards what part of itself?
The center of mass?
The center of mass. Now, for something like a planet, we are shaped like a sphere. Where's the center going to be?
The core.
The middle. Yeah. What about for me? Where's my center of mass? I don't know, probably somewhere in this area. It depends. Do you have a longer torso? Do you have a shorter torso? Are you broader? Or are you skinnier? Are you short? Are you tall? Right? You ever heard the term center of mass, right? People usually use that as an excuse for why they trip a lot. Oh, I have a very low center of mass, right? It's not really what they think it means. For our planet, though, it's in the middle. We'll come back to that idea in a moment. I have mass. You have mass. We all have mass. I have more mass than Claudia. I think that's probably safe to say, right? Why isn't she orbiting me? Why isn't she circling around me like the Earth is orbiting around the sun? Or why the moon is orbiting around the Earth?
Because your gravitational pulls are negligent compared to the Earth's. Negligent?
Well,
That's not
try
the
and
word.
make me feel
Arbitrary?
worse about myself, dude.
Wait.
Your gravitational pull is
Wait.
negligent.
Negligent is not the right word. I just realized. Arbitrary? Is that a better word?
Arbitrary.
Negligent.
You're not helping my self-esteem. No, it is not anywhere near powerful enough to overcome the largest force of gravity nearby, is what you're trying to get to.
Arbitrary the correct word?
Not arbitrary either.
There's a word. It starts with.
It doesn't deflect. It is overcome by something else. Now, I still have gravity, and believe it or not, my gravity is measurable. I can measure my gravity. I can measure her gravity. I can measure all y'all's gravity. I can measure the gravity of this. I can measure the gravity of this. I can measure all of that. But the gravity of these singular objects is nowhere near as powerful as another force of gravity nearby. What is that?
What? The Earth?
The Earth. Therefore, instead of being pulled towards me, yes.
The word is negligible.
Negligible.
Yes.
That's better. Okay. Instead of being pulled towards me, Claudia and Marquez and everyone in this room are equally pulled towards what? Earth. Diablo's going to make this difficult. All right. So here I have the Earth, right? Center of mass is right in the middle. I am here in America. I am being pulled towards where?
The center.
The center. This is the vector of gravitational pull. Abby went on vacation to China. There she is. She's being pulled that way as well, right? It's the same vector? No. Why not? Because the gravitational pull is the same towards the center of our mass, regardless of which side of the planet you're on. This is how it works for a sphere, right? So why does stuff fall and where does stuff fall? Stuff always falls towards the center of our planet. It is not down. I want you to stop thinking of things falling in this term of down. To your perspective, it is down, but that vector of movement to someone in China is off the face of the planet, right? If you continue that vector, whoop, it would go past Abby's ear on its way out to space, right? If it could go through the center of our Earth. No, but things are pulled towards the center, okay? We just think of it as down because that's our perspective. So that's gravity. Let me bring this to planetary geology again a little bit here. I'm sorry, it comes up every time, doesn't it? Pluto. What do we know about Pluto? What do you know about Pluto?
They did it dirty.
They did it dirty.
Wasn't it like once a
Did
planet?
it though? Huh?
Wasn't it like once presumed as a planet?
It has at different points in time been classified a planet. Do you know why it is no longer classified a planet?
It's too small.
It's too small. Does size really just dictate whether something's a planet?
I would think not.
You would think not. It's not so much the size itself, it's what the size does. Pluto's moon is about 30% the mass of Pluto itself. It's basically a large asteroid that got caught in Pluto's gravity. But the gravity of that moon is comparable enough to the gravity of Pluto that instead of the moon orbiting Pluto, they orbit each other. Yeah. Whoop. See, I told you to make it difficult. All right. So while Pluto is here and its moon is here, where is the center of gravity for this relationship?
In the middle.
In the middle.
Ah, the center of gravitational pull is about, oh, whoops. It needs to be closer to Pluto because Pluto's slightly bigger. It needs to be about there, which means that if you were to fly a spaceship and land on Pluto, you and your spaceship would instantly get pulled off of Pluto because gravity is pulling you towards a point in space between it and its moon. Yeah, sketchy, huh? The only way that doesn't happen is if you land on the side of the planet exactly opposite that point in space, because it's pulling you towards that point in space, but Pluto itself is between you and that.
So it would be nearly impossible to get on that planet.
Yeah,
Or
because
Pluto.
gravity is actively trying to pull you off that planet.
Yeah.
This is how gravity works. It pulls you towards the center of gravity, which in the case of a planet like a sphere is usually the center of mass. But in this sort of situation is not. Hence, this is a very large reason why it is no longer considered a planet. Its center of gravity is not its center of mass. Okay. We orbit the sun. The sun is the biggest, baddest gravitational body around. Therefore, Earth orbits the sun. The moon orbits the Earth. Why? Because as far as the moon is concerned, we're the biggest, baddest center of gravity around. Although it's in a decaying orbit, which means that it's gradually moving further and further away from the Earth. If you were standing on the Earth during the Jurassic time period, the moon would look much bigger in the sky. And then if you were billions of years ago, it would look huge. And now it looks as small as it is. 100 million years in the future, it's going to look even smaller because it's gradually every year getting a little bit further away from the Earth. I don't think there will ever really become a point in time when it just kind of like drifts off into space. Earth is still going to be the largest gravitational force. It should still stay somewhere in our proximity, as long as Earth is alive anyway, but it is ever so slowly moving away. If I were out in space without any other gravitational body anywhere nearby, I'm in dead space. Just me and this pen. This pen would orbit me because there's no other force of gravity nearby. Okay, I think I've beat that dead horse enough. Anyone want to hold him, by the way? Yes? No? All right. Just let me know. All right. So what does this have to do with our conversation today? Just like leaves fall and pens fall and remotes fall and everything falls, so do rocks. And where do they fall? Towards the center of Earth's mass, right? So gravity is a force that is constantly pulling on all of us at a consistent rate because Earth's gravity doesn't really change, right? It's generated by the amount of mass that Earth has. So as things are pulled towards the center of our planet, if they are not supported well enough, they are going to fall towards that point, following that vector. If I have some rocks just barely, oh, I should erase all that. Some rocks just kind of barely teetering on the edge of a cliffside. All something has to do is change. Something has to change just a little bit, and they will fall downward. This is called mass wasting. Gravity-produced movement. This brings up something called the angle of repose. The angle of repose is the maximum angle at which an object can be at rest without falling under the influence of gravity. Highly recommend writing that down. I'll repeat it again. The angle of repose is the maximum angle at which an object can be at rest without falling under the influence of gravity. Let's have a demonstration. Don't worry, I'm not going to drop my snake. Although I will need someone to hold him at this point.
I guess I will.
Anthony, really? Do you guys remember on day one when he was like, I'm cool with the snake being in here, but I'm never going to touch it? Look at this personal growth. I'm proud of you. All right. Hiya. Okay, where's my stuff? There it is. All right. Who doesn't like a good demonstration? Who doesn't like a bad demonstration? Those can be funny. All right. Here I have an object. It is a plane, a flat surface, which is capable of having any number of angles, right? I can spin this thing in any direction I want, right? But I have 180 degrees of possible angles I could tilt it at, right? So let's start with this object. It's a marble, right? What is the maximum angle at which this object can remain at rest without falling under the influence of gravity? What? Yeah, I have to keep it perfectly flat. Absolutely no angle. I mean, 180 depends on your point of reference, right? If this is our starting angle, we might call it 0, right? If this is our starting angle, we might call it 90. It just depends, right? But the maximum angle, this is a horizontal plane, so we'll call it 0, right? The maximum angle at which this object can be at rest without falling under the influence of gravity is 0. Any amount of tilt whatsoever, and it starts falling off the angle. Okay? Now, what about this object? It's a Lego. Ooh. There it goes. Right there. Whatever that angle is the maximum angle at which that object can be at rest without falling under the influence of gravity. Right? So what did we learn through this demonstration? The angle of repose is dependent on what? The object in question. Characteristics that determine what your angle of repose are, the nature of the object in question, and whatever your surface is made out of. In this case, it's wood, pine, right? This has a certain thing. I'm assuming that there's some basic understanding of physics here. You know what friction is, right? And all objects have a friction coefficient. Okay, the frictional coefficient between that Lego and this wood board was higher than the frictional coefficient between this wood board and this marble. Okay, so that's the surface, but what about the materials that are on that surface? What's the difference between these two things? One is not round, but a sphere. Remember? Round that's two-dimensional description, right? A circle is round. Sphere is a three-dimensional description. Good. And this is a cube. Yeah. Yeah. Okay. So we have a sphere and a cube. They're also made out of different materials, glass and plastic. But let's talk about the shape. Why would the sphere roll off at an extremely low angle, whereas this one did not?
Surface area.
Explain.
Sphere has less surface area than a cube.
At every point along the surface of the sphere, only a tiny amount of it will ever be in contact with this board, no matter how much it rolls, right? There's very little surface area to take advantage of the frictional coefficient with this surface. Whereas this cube has all the surface area of one of its sides to hold it there along that friction, using that friction. So the nature of the objects in question, what the material is made out of, all of these things determine the angle of repose, which again is basically how easily something can fall, how steep my angle needs to be before something will fall off of it. We good? We keeping up all right? Yeah? Okay. Great. Okay, now that we understand angle of repose, let's talk a little bit about slopes. The finer and rounder my sediment is, the easier it will be to fall off of a surface. The more angular and larger my particles are, the steeper of an angle they can have. So a pile of angular pebbles, for example, will make a much steeper slope than a pile of fine sand. Okay, so with mass wasting, stuff falling down a slope, let's play that as it's going. Watch how all of this material is slowly making its way down. There's no water here. I mean, it looks like there may have been water flowing there at one point, but there sure is none driving this movement. This is all gravity-driven, falling down slope. Why is stuff falling off this slope? Because that slope is not at the correct angle of repose for those objects. Look at all the other stuff that has fallen off that slope over time. Why is stuff falling off the slope?
It's not stable.
There is the word. It comes back to stability. In general, things in nature are always seeking a state of stability. That is true for slopes as well. They naturally will shed objects off of themselves in an attempt to reach that angle of repose, bless you, when nothing is going to fall off of them. Again, I'm not anthropomorphizing them. They don't have a desire. They don't have, nothing in nature like that has how do I say this? The decision-making process to make a choice. It happens naturally. This is a consequence of physics and laws that they are seeking stability, which is a beautiful thing when you think about it, really, right? Okay. This process is how we get mountains that fall and weather away, and how we can get valleys that form, and the nature in which those valleys form. Let's talk about the Grand Canyon for a second. How many of you have been there? One. All right, cool. Well, our Grand Canyon, if you ever go, you'll notice, this is a picture of it, by the way, you'll notice that it doesn't have this V-shaped valley. It does this. Boom, 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 boom. There's kind of like this slope and shelf, like that. Sort of thing. Why? Why does the Grand Canyon have these slopes and these shelves? And slopes and shelves. What is causing this phenomenon?
Mass wasting.
Sure, mass wasting. Explain it to me.
Rocks would break off at sharp angles.
Why would some rocks break off and make steep surfaces and other rocks not?
Because they're layered and the different rocks have different angles of repose.
Different rocks have different angles of repose. So I have limestone here, which has a very steep angle of repose. And then I have sandstone, which also has a steep angle of repose. And shale, a very shallow angle of repose. And then sandstone and shale and limestone and shale and sandstone. And so we get this zigzaggy cliff slope, cliff slope, cliff slope sort of shape to our Grand Canyon as the Colorado River carves through all these layers and mass wasting takes over and the angles of repose are constantly seeking to be found. Now, we live on a dynamic Earth, do we not? We've established that. Things are constantly changing, which means that every time it rains or every time there's an earthquake or every time something happens in our environment as Earth is dynamically changing, some aspect of those slopes changes as well, which means that if my slope has finally reached its angle of repose and then it rains, all of a sudden my angle of repose changes and stuff's going to fall off again. Or I finally reach that angle of repose, but then there's an earthquake. And what does an earthquake do? Shakes things. And my angle of repose is all messed up again. Stuff falls. I should make that a bumper sticker, right? Stuff falls. You know, like the stuff happens ones, but it's stuff falls. Y'all would get it. You'd laugh when you see my car. All right. So these mass wasting effects often result in what we consider to be disasters. A disaster is a man-made concept. It wouldn't be a disaster if we weren't there for it to be a disaster too, right? Mass wasting effects like landslides, for example, have happened forever. But I mean, I doubt the mosquitoes ever thought of them as a disaster, right? So just something to bear in mind. There are multiple cases of terrible, terrible landslides that have killed a lot of people. There are some places where they've happened fairly often: India, Pakistan, the Philippines. I'll give you some closer to home examples here in a minute. But what happens to cause a landslide? Your angle of repose has been surpassed, and stuff has to fall off that angle for it to reach a stable condition. This can be triggered by things I already mentioned: earthquakes, rainfall. What does rainfall do that could cause this? Y'all ever tried making a sandcastle? No? Never used like a sand pit? Yeah. What happens when I try making a sandcastle out of dry sand? Yeah, I just get a pile of sand. It won't stay in a castle shape. I need it to be a little bit wet. If it's a little wet, then there's a little bit of stickiness to my sand, and it will maintain the shape that I give it. But what happens if I put too much water in it? I get a sloppy puddle, right? That's what happens to all sediment, believe it or not. If I put just a little bit of liquid in there, it tends to stick together pretty well. But if I saturate it, give it a lot of rain for long enough, it falls apart. Guess what? If I lose all the friction between my sediments and between my layers of sedimentary rock on a slope, then all of a sudden my angle of repose, which may have been fairly high, drops significantly because my friction coefficient has dropped significantly. And stuff's going to fall off that slope to try and reach that new angle. This is a landslide. Okay. Deforestation can cause this too. Why? Because roots bind sediment and rock together. You remove that, all of a sudden, there's not that much anchor, and you lose stuff off your slope to reach a new angle. Okay. This is La Conchita in California, 2005. This entire slope fell down and completely destroyed this whole part of the neighborhood. Now, why did that happen? California doesn't get a whole lot of rainfall, right? But they got a very heavy rainfall season, a week solid, I believe, of just rain. And it saturated the sand and clay in this hillside, which meant that the angle of repose had to change. Shoom, everything fell down. Gravity. Stuff fell. Totally bulldozed all those houses. I told you about the town I used to live in Washington by Mount Rainier, right? Ording, where we did the Lahar drills and all that stuff, right? There was another town not too far away called Ozo. And while I was living in Ording, there was a landslide in Ozo. Now, it rains in Washington all the time. They only get about 40 days of sunlight a year on average. The rest of the time, it's either cloudy like this or it's raining cats and dogs. But there was just heavy downpour day after day after day after day. And this escarpment here got so saturated with water that it collapsed, fell down into this river valley. And as it carved its way down into this river, it shoved all the river water out, kind of made a micro tsunami, and all of this went into this town of Ozo. Everything that you see here that's red is a house or a business. And this is what Ozo looks like now. Totally gone. 43 people killed. This is the deadliest landslide so far in U.S. history, as long as we've been recording it, as long as the U.S. has been a country. I remember that day, everybody, because I mean, these towns are close enough that they've got friends and family, you know, in each other's towns, right? Everybody in Orting just like booked it out of town. I was just walking along the street, minding my own business. I wasn't from there, so I didn't really know what was going on. But all of a sudden, just every car in town just zoomed down the highway. I'm like, what is going on? And then I found out. All our first responders, everyone who had any friends or family members in Ozo, they were all booking it down to see if they could find anyone that survived. It's pretty crazy.
Wait, so was it the entire town? Was that?
This entire part of the town, yeah, there were a few structures out here, a few structures out here, a few structures across the river that survived, but most of the town got wiped away. 43 people died, way more people were injured. It just so happened that a substantial number of people were out of town for the weekend. Yeah. Okay. Now, there are softwares that we can use, programs called Geographic Information Systems, GIS. Do you have ever heard of GIS? A lot of you may actually end up using GIS for one reason or another. It's not only applicable in geography or geology, it's used in biology, it's used in government, it's used in policy, it's used in anthropology, it's used in agriculture, it's used in a whole bunch of, it's used in history, it's used for so many different reasons. It is multi-applicable. So you will probably end up using some aspect of it or using data from GIS at some point in your careers, no matter what it is, okay? But we can use GIS softwares to input data sets and then see how those data sets relate to each other in a physical setting. So I could put in a data sheet, say an Excel spreadsheet that has the average rainfall density of every location in the United States for the last 10 years or 20 years or 100 years. All of that is something that you can store on a data sheet. I can input that in my GIS software, and then I can input, say, a topographic map, the elevation data for everywhere in the United States. And I can put that in my GIS. And then I can input where are all the running water, where are all the lakes, where is all the rivers and the streams and all of that in the United States. And I can input that. And I can throw all of this data onto a map and then color code every designation of rainfall density or elevation or running water depth or anything like that. And I can color code all of it and then tell it to, bless you, to match it all together and tell me all the places in the US where all that data overlaps. So if I'm interested in seeing all the places in the US that have heavy rainfall, lots of running water, and high elevation, I can get a map that looks like this. It's a hazards analysis map. As you might imagine, green means moderate potential, the red means very high potential. These are landslide hazard data sets here. Now, why would rainfall mean the potential for a bigger landslide or for a landslide at all? What did we just talk about? What does rain do?
It saturates the soil.
Yeah, it saturates the soil and removes that friction. Yes. Okay, what about running water? Your water's running, you better go catch it. Right. No? No. Yeah, I'll admit that was a no. All right. What if a river starts to weather away at the base of a cliff? What's going to happen to the top of the cliff? Yeah, my river is removing material from the bottom of the cliff. Eventually, what's going to happen to the stuff at the top? It's losing all its support, right? It's going to fall down under the influence of gravity. Running water removes supports. Okay, so that's also very relevant. What about elevation? Why would elevation matter for a landslide potential?
Because that's where stuff can fall from.
Yeah, my pen will never fall off this table as long as it is on that table without any potential of falling off of it, right? But if my pen were, say, right here, is there more potential for it to fall? Right, it takes a lot less for that to happen. Without elevation, stuff can't fall in the first place, right? So those three factors combined on this geographic information system software, and you end up with a map like this. The Appalachians, whew, you got a lot of running water, got a lot of falling water, right, like rain, and you got a lot of elevation. There's a lot of landslides that happen out here. As you can see, we are in a lot of danger over here, right? This could happen anytime. We get so much rain. We have so many rivers, and there's elevation for days out there, right? So we're pretty much okay out here, but this is a good thing to know if you're ever interested in, say, buying a home somewhere. I want to move to Virginia and buy a home. It's useful to know how to get this information from different agencies. They will provide you this information so you can see what sort of, say, hazards are possible in this location that you could buy your house in. Environmental hazard assessments are very, very good to find. Yes. This is a landslide hazards map. But this practice in general is called environmental hazard assessment. And whenever you buy a home or a business, if one has not already been conducted for that area, it's very useful to hire someone to give you one. Helps with knowing what sort of insurance you need, for example. Okay. So how do we classify these different landslides? We give them different names based upon a few factors. I've been using the word landslide a lot. Just kind of a general catch-all. But that's an example of the way that we name these things. Landslide. The first part of the name comes from the material. Is it debris? Is it mud? Is it rock? The second part of the name comes from the type of movement. Is it sliding? Is it falling? Is it flowing? Mud, flow. Rock, fall. Debris, slide. That's how we get these names, okay? So you can have unconsolidated things, random debris, mud, maybe like a lahar, right? Bedrock, when rock is just sliding on top of rock, for example, just hard rock layers, that can happen. And then you've got falls, slides. A fall is when it's actually just going through the air. A slide is when it's following along a zone of weakness, maybe like a fault, for example, as it moves downhill. Flow, this is usually when it behaves like a fluid. Maybe it actually has water or enough air in it to behave like that. Or if you give some solids enough energy, they can actually behave like a fluid. Think sand, for example. Have you ever seen a dump truck dump out a whole bunch of sand? If you're not careful, you can get buried in it. It behaves very similarly to water, for example. When you give those particles that much energy, they behave very similar to the particles of a fluid do. So, a couple of examples here. We have two different types of landslide. Rotational landslides are where the gravity of movement downhill starts, but as all this material is moving downhill, it compacts the ground underneath of it to the point where this becomes so resistant to movement that this moving material has no choice but to kind of push its way out onto the surface. Okay, so you get this sort of cup shape. This is called a rotational slide. So it starts going down and then gets shoved out onto the surface. Okay, And then you have a translational landslide, where it's just a straight shot, layer on top of layer, following a straight linear plane downhill. Translational and rotational. Any questions so far? All right, well, I'll show you some examples then. This is a slump, a rotational landslide. So as you can see, we've got these couple of different sequences of material just kind of falling down. This usually happens when it's saturated, right? So it slumps down, makes that cup shape, and then gets shoved out onto the surface. This is a real life example of that. You can see the different steps as each section kind of slumped down. Now, the getting shoved out onto the hillside isn't really apparent. What can you see in this picture that may have caused this to happen, this movement?
A river.
A river that did what?
Eroded away.
Yeah, it could be a river, it could be the beach, that could be the ocean, but whatever happened caused material to be removed here, right? And removed the weaknesses or the structural supports here, and this slumps down, okay? So you see the picture, and you can interpret what the most likely cause was. Now, when they built that road there, do you suppose that they figured that potential for this to happen was there? No, as a matter of fact, when they built that road there, this cliffside was probably significantly further that way. Okay. Rock slides. This is what happens when a layer of rock slides on top of another layer of rock. Oftentimes, it's because water gets between the two layers of rock. Real life example, Gravant, Wyoming. Probably the largest rock slide that I can think of, which it doesn't look like that's how you should pronounce it. It's Grosventree or Tre, but it's French. It's Gravant. Don't ask me why. It's French. All right. But what happened here was we have a layer of sandstone exposed at the surface on top of a layer of clay. What do we know about clay? Does clay let water slide through it very easily? No, it's hydrophobic. Flat layers of clay on top of each other tend to prevent the passage of water, right? So sandstone, on the other hand, absorbs that water, holds it within itself. And so we have a lot of rain that gets absorbed by the sand, cannot pass through the clay, and that buildup of water between clay and sand caused a big chunk of the sandstone on this hillside to slide over the clay bed downhill. How big was this? Well, here's a scale bar. This is 1 kilometer. So that was about 3 kilometers of sandstone that slid an additional 3 kilometers down into this valley. I can't even imagine how loud that must have been. All that rock moving downhill all at once must have been deafening. I have been here. I've seen the landslide, but it happened long before I went, right? However, you can see this in practice. If you ever are driving along the highway and you see the signs that say, beware of falling rock, you ever seen those, right? Watch for debris on road, things like that. That's usually an indicator that the engineering corps who built that highway didn't bother consulting a geologist. Because what will happen is if you build your road along the sides of the mountains where the layers of rock are parallel to each other, there's the potential for rock slides. One layer slides down the hill on top of the other layer, like this. Whereas if I build my road on the sides where the layers of rock are like that, there's no potential for any one of these layers to slide downhill. You still have falling rocks, but not entire layers of them. Yes?
That just sounds like Colorado.
Yeah. Colorado. There's a lot of this in Colorado and California, and yeah, you can always tell. But that's why, okay? If you ever, any of y'all go on to become road engineers, just bear that in mind. And then there are debris flows. This is unconsolidated stuff, right? Like mud, random debris, like a lahar. A lahar is a type of debris flow. A bunch of things that are flowing downhill under the influence of gravity. Now, water is often involved, but not the driving force like it would be in, say, a river. Okay? When that debris reaches the bottom of whatever it's flowing down, usually a mountain, then all that energy, that gravitational energy, is instantly lost because there is no more downhill for it to go. Everything spreads out and is deposited. We typically will refer to that as an alluvial fan. Whenever debris is deposited at the base of an elevation because it has lost energy, we call it an alluvial fan. Earth flows. Think of this as kind of a slow motion landslide, right? Where you have soil that is always very wet, very saturated. And so over time, it slowly makes its way downhill. Kind of like, this probably took 20 or 30 years for all of this to make it down to the bottom of the hill. Okay, it's just that those top layers of soil that are constantly wet enough that they can't hold enough friction and they just slowly tumble down there. And then there are creeps. And as the ladies know, creeps are everywhere. I'm not even joking. These things are everywhere. If you've ever noticed that a sidewalk is kind of off kilter, like you just walk on the sidewalk and then it does this for some weird reason and you don't know why, it's because there's a creep under it. If you've ever noticed a fence line, it's like it's a straight shot and then all of a sudden goes off that direction for no reason whatsoever, there's probably a creep. A street sign has been twisted. The base of it has been twisted around. It's probably because there's a creep under it. So what is a creep? When you have a person who stares through your window, no, that's the wrong creep. But whenever you have the first top layers of your soil that freeze, okay, they freeze, and what happens when water freezes? It expands. Yeah. So as that water and that soil is expanding, it is slightly picking up the stuff on top of it. Streets, sidewalks, signs, fences, all of that. It slightly picks it up, but then when it thaws, what happens? That stuff moves back down with the soil. However, here's the thing. If I'm on a slope, because of the nature of ice, it will always freeze at 90 degrees to the angle that it is sitting on, right? So my ice in the soil, if I have a slope like this, the ice is going to form 90 degrees to that angle, right? But where does gravity cause things to fall back down to? Towards the center of the planet, regardless of the angle. So when things fall back down, when the ice thaws, it's going to be a little bit further downhill. And so year after year, freeze, thaw, freeze, thaw, freeze, thaw, stuff is going to be moving along like that. And as this happens for decades, that movement becomes noticeable. Here's an example. This picture was taken in 1971. You can't see it very well, but you can always look at the PowerPoint later. Here is one side of the curb, and there's the other part of the curb, offset maybe by a few inches. In 1974, that picture was taken again. Someone thoughtfully painted this one red. Very convenient for us, right? There's one side. There's the other. A few more inches. 1993, year I was born, for anyone paying attention, right? Here's that, and there's this. They aren't even touching anymore. And then in 2005, there's a couple of inches of separation between them. Why are these two curbs getting further and further away from each other? There's a creep under them. Okay. All right. And then solifluction is very similar in nature to earth flows and creeps. This typically happens whenever you have permafrost. You'll know what permafrost is? Permafrost happens way up north and way down south, wherever it stays so cold throughout the year that only the first few inches of soil can be unfrozen at any time. Okay? Everything below those first few inches, still constantly frozen year-round. So those top few inches of soil will move downhill on top of the frozen soil underneath of it. And so you get something that looks like this. They look like frozen waves almost, like waves in the soil. This is solifluction, the downhill movement of soil on top of a harder surface like permafrost. Okay, that's mass wasting. Any questions about mass wasting? Great. Let's talk about running water then. About 97.2% of all water on Earth is in the ocean. Of the 2.8% that's remaining, 2.15% of it is in glaciers, which means that only 0.62%, well, no, 0.62% of the remaining is groundwater, which means that, let's see, 0.62% plus that's 0.77%, right? Of that 2.8, which means that only 0.03% of all water on Earth is running fresh water. 0.03%. It's not much, is it? When you put it in that perspective. Something we take for granted every day. Y'all have water bottles in front of you. Running fresh water is extremely valuable. And unfortunately, something that is becoming harder and harder to find. Y'all take those water bottles for granted, but 20 or 30 years from now, you may remember a time fondly when you could just throw a half-empty water bottle away. Yeah. All right. Now, we start off by studying how that water starts to run, I suppose you could say. When water falls as rain, it gets collected somewhere. It goes from a high point to a low point. The area in which it falls and begins that flowing process is referred to as a drainage basin. We separate drainage basins into areas, usually separated from each other by zones of high elevation. So this ridge on this mountain might be a divide. This ridge on this mountain might be a divide. Everything that falls between, all rain that falls and flows between these two ridges, we would call this a drainage basin, for an example. Okay, so we have lots of drainage basins in the United States, the largest of which is the Mississippi River Drainage Basin. Why do we call it that? Because every raindrop that falls in this huge area of the United States ultimately makes its way out through the Mississippi River in Louisiana. All of it makes its way there. I mean, all the stuff that's not used, but you understand what I'm saying, right? We divide the Mississippi River into smaller drainage basins. For example, we've got the Missouri River, the Upper Mississippi, Arkansas, Red White, Ohio, Lower Mississippi, so on and so forth. This is a way for us to determine, to keep track of how much water falls and flows in these areas and where it goes. Kind of keeping track of it, accountability for it. Because it is such a precious resource to us, we like knowing how much there is and where it's going and how pure it is and all that stuff. Okay. Let's talk about the mechanics of flowing water. How many of you have ever walked out into a stream? No? Probably the wrong crowd. Yeah, into a stream. We don't have that many around. You have? All right, well, Alyssa, you can help me out with this then. You start off right at the edge, and then you walk further into the stream. What happens? Yeah, the further out into the middle of the stream you get, the stronger the current gets, right? Why? Why is the fastest flow, the most energy, in the middle of my stream? Why is it not evenly distributed across the entire thing? Any ideas, Abigail? No? What do you think? Nothing? What's happening on the sides of the stream versus what's happening in the middle?
Is the water on the side pushing the water in the middle?
No. Not really.
Is it
Yeah.
the friction
What?
Of the energy diffused the further away it is from
What is energy being diffused on?
the ground?
The ground, the rocks, the structures, everything that's on the side of the banks of my river is absorbing energy. Whereas in the middle, where the river is deepest, there is less stuff absorbing the energy of flow. Therefore, the further out in the middle you get, the faster the flow gets. Does that make sense? Yeah? What if I don't have a straight river? What if my river does this? It's a snaky sort of river. On the straight-ways, yeah, it makes sense. My fastest flow is in the middle. But what happens when I go around the edge? Is my river still going to be fastest in the middle? No. Where is it faster? Is it on the inside of the curve or the outside of the curve? Why the outside of the curve?
Because there's a lot more force on the turn.
Yes. As I have more force in the middle of my river on the straightway, it encounters this curve, and it's not like the river is saying, oh, here comes a turn. Make sure you direct the energy that way. No, it slams, the vector of its movement slams into that edge and has to get shoved around the corner. And where does that happen? On the outer edge of the curve. As that happens, it eats away, weathers away at the outer curve of our river, pushing it out. We call that a cut bank. Okay. Now, on the inside of the curve, because that's where the energy is slower, we get a buildup of material that has been carved away from the cut banks further upstream. We call that a point bar. So our rivers are constantly pushing further and further out along these curves. If you want to imagine what this water is doing, just think of yourself in a car. You're driving along in a car, 35 miles an hour. Oh crap, that's my turn. What direction does your body go? If I'm turning right, my body goes. What direction does it feel like your body's going? Is it going left? No. Gotcha. No, my body is still trying to go along the same vector of movement it was before. Why? Because my body's not the car. My car might be going into the right now, but my body feels like it's going straight forward in the direction it was before, which according to our car's new orientation is our left, but is really just the same direction you were going before. That's the same thing that's happening here. The water is going this direction, and then it slams into that wall, shoom, that way. Its force still wants to go that direction, but it's being forced to go that way. It's being shoved that direction, which means that all that energy is being expended on the cut bank, pulling material off of it, breaking material off of it, weathering it down. I have a model here that's going to show you how this happens. Now, you're going to see that on these outer edges, the river is eating material away. And on the inner edges, it's depositing it again. But the overall effect is that more and more material is carried downstream, resulting in a river valley. Something else you're going to notice. Once one of the bends in the river moves far enough away from the central course of the river, that bend gets abandoned and the stream snaps back close to the middle before starting to make another curve out this direction. Okay? It's got kind of a preservation of energy thing. It can't move too far away from the central course of the river. Okay? Check this out. And then it's going to get abandoned and snap back towards the middle. Chewing away, removing material on the outer edge, depositing it on the inner edge. But notice that as time goes on, our valley itself slowly gets deeper and deeper and deeper as more material is carried further and further downstream. Yeah, it's cool, huh? Okay, so that is how running water weathers material and carries it away. Erodes, right? Now, there are three different types of erosion that we can have in our water. There is your bed load, which are the heavier materials that get pushed along the bottom. Okay, like your typical river, like you might imagine gravel. Then you've got your suspended load, the things that are small enough that your water has enough energy to carry them in it. If you've ever seen really cloudy water, that's usually water that has enough energy to carry those clays and sands and things within itself, and that's making the water cloudy. And then there's the dissolved load, all the chemically dissolved components, the calcium carbonate, the silicas, all that stuff that makes Odessa water taste so yummy, right? Dissolved load. I like to call Odessa water crunchy, right? And then when all of that gets deposited, as my water loses energy, again, this is where we get that alluvium, like where we got that alluvial fan before that we talked about. That deposited material we call alluvium. Now, when that alluvium is deposited in another larger body of water, like when a river runs into an ocean, for example, we get a delta. If you've ever been to Louisiana, or even seen a picture of Louisiana, you've seen a delta. Here we go. The Mississippi River runs into the Gulf of America, and I don't know if I'll ever actually be okay with that. Anyways, so it gets deposited out there, and as it does so, it drops all of its load, bed load, suspended load, and dissolved load, and builds up this delta, pushing further and further out into the Gulf. Okay. Levees are structures that are formed along the sides of our rivers. Every time a river floods, it pushes sediment out of the river and onto the sides, onto the banks, which builds up the sides of the river, which make it a little bit harder for it to flood the next time. And then the next time it deposits more stuff, and the next time it deposits more stuff, until finally, if a river is around long enough, it has built up naturally higher banks, walls along the sides that prevent your normal floods. Really, only really big floods can flood whenever you have a levee. We've actually learned from this. We can now make artificial levees along the sides of valleys, and they even work half the time. And then this is what an alluvial fan looks like right here. Okay, so you can see this steep mountain stream carried a bunch of material down here, deposited it all here where it got flatter, and now you have this alluvial fan. All right, how many of you have had a flood since being here? I mean, if you've grown up, you've seen a lot of floods, right?
I had a flood in Midland once.
You had a flood in Midland once.
It
Wow.
was at my apartment complex.
Wow. Have your houses ever flooded? Yeah, mine too. It's not great. Why? Why are there floods? What makes things flood?
In Odessa?
In general.
There's nothing to drink.
Claudia,
but
you
water.
good? You good? All right. Yeah.
Undersaturated soil cause of that.
Undersaturated soil?
Yeah, as it doesn't absorb as much water as like it usually should in other places that are less dry.
If there's nothing to drink up the water.
Nothing to drink up the water. Well, nothing's drinking it. Is there a different word you could use? Absorb is a much better word to use. There's nothing to absorb the water. Is that what you're going for there, Ray?
Yeah.
Something similar to that? Okay. So we do have soil. It's just not good at absorbing the water, right? There's a lot of clays and stuff, and it's not great at absorbing that water. And so it tends to flow over, and we don't have great
Flood infrastructure.
yeah, their infrastructure is not really good. Our water mains break down 2 or 3 times a year, right? We have infrastructure that cannot support that much water. This is true in nature as well. This happens in nature. This is what a flood is. When so much water goes into a water vessel that it cannot contain it. I have a glass of water here, and I start pouring water into it. it'll overflow eventually. If my water input is greater than the water storage capacity of my vessel, it will overflow. That's true for sewer systems, and it's true for rivers. If a river can only hold 100 meters cubed of water per every foot or whatever per meter of distance, and you get 200 meters cubed of water flowing, you're going to have a bad flood. I just last week I did a project for the class I'm taking. It's about environmental risk assessment. I used GIS software, like what I just told you about, to determine what the flood threat would be to the city of Grand Forks in North Dakota if X amount of water were to go into it, into the river over there. And I did it with, 5 different levels of water going into that river. And the last one was the entire region was covered in water, which actually happened in the early 2000s, I want to say, was a flood that bad that covered basically the entire city in water. It was bad. These things happen. So studying them is important, why they happen and how to prevent them, how to try and predict when they'll happen or forecast, and then try and stop them or divert them. So what can cause floods? Melting snow. Your normal amount of water that's flowing through an area can have a lot added to it if you're also taking into effect melted snow. Heavy rainfall, uncharacteristic rainfall, right? Adds enough water to make a problem. A flash flood. If you're in a place that does not have good enough drainage, flash floods can happen. I was on a fossil dig in Utah in 2016, and we were camped out on top of a kind of a little mesa, okay? So this region that we were fossil hunting had a bunch of mesas like this, and one of them we found was kind of shaped like that. So we pitched our tents up here, right, and parked our equipment trailer up there. That night it rained. This is the middle of the desert in Utah. Water doesn't really seep in. It's very similar to here, right? And so it rained, and I heard this all night long, basically. And the next morning I went out, and the entire landscape had changed. Like some mesas had lost a lot of material. Gigantic boulders that were there one night were gone. New boulders that weren't there before were there. And the water line had come about 20 feet up our mesa. If we had decided to pitch our tents on the ground, if we hadn't found that one, I wouldn't be here talking to you tonight or today, right? Flash floods, they happen, and you got to know where they might happen and how to avoid them. They can also overwhelm dams. Dams are often used to help control excess water flow. Well, if I have a flash flood or any flood whatsoever that overfills my dam, it can break that dam. This happened to the Grand Teton Dam in Idaho. The entire dam fell apart. It broke. It was overwhelmed and flooded many towns downriver, causing lots and lots of damage. So, besides using dams, how can we try and control floods? This is what an artificial levee looks like. You ever go to Louisiana, New Orleans, you'll see these everywhere. They build these up to try and control overflow or even just normal flow. Another way that we can prevent floods from happening is by making sure that the waterways that do flood are deep enough that it can accommodate the amount of water that we want it to. Rivers beds tend to fill up with sediment if we're not careful, which is why they will often change course. If it's not energy efficient to continue along the same path, it will change course to a new, more energy efficient route. So if we can keep digging out and dredging the sediment from the bottom of a body of water like a river, then the river will continue to go along that course because it can be accommodated by the space. We call it channelization. Flood control dams are supposed to work by absorbing all the flow from the flood and then slowly releasing it over time. That works great until it doesn't, as do all of these methods. All right, any questions about running water or floods or anything? Yeah? You good? All right, groundwater. Remember that statistic I gave you before? How only 2.8% of all water on Earth is fresh? And now that 2.15% of it is groundwater. The vast majority of all our groundwater, of all our fresh water, is in the ground. Okay? It's what we drill wells, water wells for. Okay? So most of that water is goes into irrigation. Okay? Agriculture, keeping crops alive, keeping herds alive. And then a bunch of it goes into public works, keeping sewage and sewer systems going. And then the rest of it goes into drinking and bathing and all that stuff. Your pool, if you happen to have a pool, or the city pool, okay? It is groundwater that is responsible for carving out caves. Remember, if you have carbonic acid or sulfuric acid that's dissolved in your groundwater, it is going to dissolve away your limestones and make these caverns. Oh, by the way, I scheduled my spring caving trip, beginner's caving trip for, I want to say April 11th. Should be a Friday. We'll be leaving here at 1 p.m. We'll be meeting out at the Globe Theater. I'll have a bus out there. I can take students. I just need liability waivers signed. I am also limited to 15 people because more than that in the cave and it gets real stuffy, right? And it takes forever and we don't want it to take forever. I'd love for everyone to be back by 6 o'clock that night. It's usually about a 5-hour trip. If anyone is interested, let me know. I'll make a note. There is obviously a physical requirement. You need to be able to lift your own weight because there is some rope work and there are some ladders. You need to be able to fit through a space that is approximately 1 foot. It's a crack. It's not a hole. It's a crack. You just need to go sideways, but you do need to be able to fit through that. So yeah, there are some size restrictions, and obviously if you're claustrophobic, it might be a challenge. There is the potential that there could be rattlesnakes, but I always check. I always go in first just to check, just to make sure. If you're interested, shoot me an email or let me know in person. Okay, now groundwater is stored in the rock itself. How does that happen? Well, even though the grains in our sedimentary rock are so tightly compacted, there is still space between them. That space is what we call porosity. Think pores, okay? It is porosity. The amount of porosity that a sedimentary rock has determines the amount of fluid it can hold. Permeability is how interconnected those pores are. It's all well and good if my rock can hold liquid, but if it can't transfer that liquid, what do? Well, for oil, we frack it, right? But for just in nature, it can't move anywhere. So you can fill it with water and then that water just stays there. So ideally, for good reservoir rock, we're looking for something that has a good balance of porosity and permeability so that it can store and move that liquid naturally. How do we access it? Well, we drill our little straws down there, right? Our water wells. The point underground, the line underground beneath which rock is constantly saturated is called the water table. If you've ever heard that term before, that's what water table means. It is the line underground beneath which water has saturated the rock. Rivers, lakes, all of those are constantly trying to reach the water table, okay? A lake exists in the first place because that level of your lake is usually where your water table's at. A river is carving its way down to the rock in an attempt to reach the water table. It is possible to have water, artificial or not artificial, but small scale water tables higher up in elevation. That occurs when you have a layer of rock that does not let water transport through it easily, say like a clay bed, okay? We call that an aquitard, and it prevents rainfall water that has seeped into the rock from going anywhere else. And so that's how people who live up in like the mountains can have relatively shallow wells. You just got to locate one of those perched aquifers that are higher up in elevation. Traditionally, though, most wells do go down into your main water table area. If you've ever heard of a spring, there is a rumor, or I guess I should say a long-lived myth, that springs are where underground rivers come out. They look like this. There is no such thing as an underground river. Occasionally, water will flow through a cave, but not for very long. And it is not a river that just goes for miles and miles and miles. There's no such thing as an underground river. There is water in pores in the rock. And when, bless you, when your aquifer is exposed at the surface, that water is pushed out of the pores in your rock and makes a spring that looks like this, which is where the myth of underground rivers came from. I had a student a few years back whose dad's entire career was based on dowsing. You ever heard of that? A dowsing rod? There's people who think that you can take 2 copper rods and you hold them close together and then you just kind of like walk around and you can locate underground rivers. And then you drill there and naturally water comes out. Yes, water's going to come out because you drill down deep enough and you find the water table. I won't say it's a form of con. They may earnestly believe they know what they're doing, but there is absolutely nothing behind it. There are no underground rivers. So, but man, I was teaching about this and she was like, no, there are underground. My dad dipped it. I was like, anyways, okay, so that's what a spring is. Now, why does the water get pushed out of the ground? Because of the natural pressure that's on it. Anything underground is going to have a lot of pressure on it, and it's shoved out of the pores in the rock, making that spring. We can use this. For example, if I have 2 layers of shale, which are going to prevent the passage of water above or below, and then a layer of sandstone between that shale, then that sandstone is going to fill with water, because it's exposed somewhere at the surface, presumably, okay? As it fills with water, it basically becomes a compressed layer of water-rich rock. That water can't go anywhere. And so if I then later on drill my little straw down into that, right, that water's going to come out under its own pressure. If I just go into a normal water table, I have to use a generator to pull that water out. It's not under enough pressure to come out on its own. But if I find one of these confined, we call them artesian aquifers, it comes out under its own pressure. Why? Because that water is going into the layer of rock up here at the surface level. That's where the water wants to be. Because it has been forced underground by the pressure, it is still trying, if it could have its way, it's under enough pressure that it would still come up and reach that water table. And so if I drill my straw down there, my water well, then it's going to come up under its own pressure in an attempt to reach that water table up there. That's an artesian aquifer. Those are great. Money. Fantastic. Everyone loves those because it doesn't take any energy to bring the water out. Okay? Like it does for a traditional water well. Now, we've actually learned how to use this principle in our everyday lives. You may not even realize it. We call them water towers. We have a bunch in our cities. What do water tables do? Why would we store water so high up instead of, it's got to be more convenient to store it down below, right? What we're doing here with our water tables is the well pumps water up here into this giant tank. And then it is piped from the tank to our homes and businesses. But because this water that is piped away is stored up here, then whatever the water level is in this tank is the artificial water table that this water is trying to reach again when it comes out, which is why we have pressure in our showers and our baths and our faucets. That's why I have pressure here if I were to turn it on, but I won't because I've got stuff in that sink, right? It comes out under pressure because it is trying to go back up and reach that water table that we have artificially made for it. Water is very important. Why? Well, we drink it. We bathe in it. We're 70% it, right? It's very important for us to take care of our water. So that's why things like toxins in our water and pollutants and all sorts of things are very concerning to us, okay? Water in the ground is technically renewable in the long scale, the long term. But as far as you and I are concerned, we really should be thinking about it as non-renewable. Same as oil. Oil takes millions of years to make, but technically it will be renewed over millions of years. Water technically renews itself in the ground, but we pull it out at twice the rate that it is renewed. This is the High Plains Aquifer right here. Everywhere you see in yellow, the water table has dropped 25 to 50 feet. In red, more than 150 feet, right? We live out here. There's some yellow, mostly white. The white means it's dropped about 10 feet. But this map is about 15 years old. It's gotten worse. During the summer, I work for a landscaper when I'm only teaching one class online and I still have to pay bills, you know. I work for a landscaping company. And we do general maintenance as well. We install AstroTurf, we install sod, we do all that stuff. But also, a lot of the other companies that we do some close business with, they do other homework like drilling wells. And this last year, I heard more people in town say our well went dry and we had to re-drill it than I have ever heard before. What's happening? We are pulling more water out than comes back in. So we got to drill our wells deeper. Well, you can only drill so far before you hit rock, crystalline rock that is too dense for water to be in it. You've exhausted your water table, and what happens then? You got to bring water somewhere else, from somewhere else. Several towns in America are already in that state where they have no water and it has to be piped in or trucked in from somewhere else. What happens when that becomes commonplace? When that's the normal? This is the thing that we're going to be struggling with. That's why I encourage as many of my students as are interested in geology to maybe consider hydrology. Because I can foresee a day when a hydrologist that can find people water is more valuable than a person who can find us oil. Because when it comes down to it, would you rather pay $1 for a glass of water if you're dying, or a buck for a gallon of gas in your car? Right? Everyone will always go to water. I'd rather walk to work every day if it meant I had water, you know? So I'm not saying it's going to look like Mad Max, but I don't know if it'll be far off. Okay. When that water gets heated up, it creates what we call hydrothermal activity. Okay. This is where you get your geysers and your hot springs from. It is that groundwater that is heating up and shooting up out of the ground, right? They actually use this in Iceland. They have a geothermal power plant next to Reykjavik, the capital. Okay, there's a picture of that power plant. I've been there. Okay, this power plant, you'll notice that steam's coming out of it. This power plant taps down, goes down into a water reservoir that is close enough to a magma chamber that water is hot enough that it should be steamed, but it's too pressurized at that depth to become steam. So what happens when you drill down into it? It comes up as steam because all of a sudden you've given it an access to lower pressure. What do you do with that steam? You use it to turn a turbine, and that generates electricity. Geothermal power plant. Very useful, very good, very clean. Among the cleanest possible energy sources. Okay? But also, they take a lot of that hot water and they pipe it through a bunch of their buildings in the city. Keeps them nice and toasty in the winter without needing any like air heating. Okay? And whenever that water dissolves enough material underground and makes those cave networks, occasionally the ceiling of the cave collapses. And when that does, it makes a sinkhole at the surface. Okay? Whenever material dissolves underneath the surface, the top can collapse down into it, and it's kind of like mass wasting, right? And that makes these sinkholes, which are all well and good when it happens, and the only people that care are the sheep. But when it happens under your house, that's a whole other story. again, another example of why an environmental hazard assessment might be a good idea. All right, any questions about today's lecture? Yeah.
Is there like any signs before that happens, or is it just like I don't know?
Yeah, you can figure out what the layers of rock under your house are like. When you hire someone to do an environmental hazard assessment, it's usually full spectrum. They'll tell you about things like landslide potential, subsidence like this, water quality, all of that stuff. How are we doing? Any other questions? Great. All right. Module 2, off to a great start. One could say a rockin' start. All right. I'm going to end the recording here.